So looking more closely at the light beam and our rockets, the green line links two events that are simultaneous in the reference frame of the rocket ship. So that is, those two events occur at the same time. So what that tells us is that for an object travelling with a relative velocity v, the time grid lines have to follow that green line. So that is, the time grid lines have to look like this. And that means then that for our object travelling at the relative velocity v, the x dash axis is parallel to those grid lines and looks like this. And we also know, so one of the postulates of relativity, that the speed of light is always equal to c. So that means in any reference frame, the gradient of c must be 1. So for an object travelling at some velocity v, after 1 second, the light has travelled 3 times 10 to the 8 metres. So that's here on our purple arrow. And that means that this point on our light curve, the end of that purple arrow on the yellow curve, must correspond to 3 times 10 to the 8 metres. So that would be here. And the same goes for 2 seconds and so on. And that means then that our vertical axis is the grid line that goes through 0, just as in any other graph we've ever drawn. So that's this guy here. So from the point of view of a stationary, So from the point of view of our stationary man, we represent an object moving at some velocity v using this red axis. So for the object moving at some velocity v, that red axis is the reference frame of our rocket ship travelling at some velocity v. So in that reference frame, the laws of physics still hold, and the speed of light is still a constant and equal to 3 times 10 to the 8 metres per second. And we can see that this axis is warped compared to our stationary observer. And that causes some interesting looking effects on the way time and distance must behave in this red reference frame compared to, or from the point of view of the blue reference frame. But we'll look at those a little later. So we have our axes for our object that's stationary. So from the point of view of the blue man, we have ct and x. And we have our constant, which is the speed of light with a gradient of 1. As the speed of some object travelling past us increases, we represent it like this. And the faster it's going relative to our reference frame, or relative to the stationary reference frame, the closer its axes move towards the speed of light, and the more warped its grid lines seem to become. In these last 2 videos, I would imagine that you've had a bit of a mind twist. And that's quite understandable, because until now, your worldview and your understanding of physics has come from 20, 30, 40 odd years of everyday experiences. And in this video, or in this topic, we're trying to grasp that actually that experience, which for us is so common and so normal, is actually only correct for a very small number of circumstances. And the rest of the universe doesn't behave as we see it behave every day. And to become comfortable with that idea is going to take some time. I mean, we have to counteract, as I said, something like 40 odd years of experience. So the key point to remember is that all of these conclusions are based only on the 2 fundamental principles, that the speed of light in vacuum is a constant under all circumstances, and that just like the speed of sound in air, and that the laws of physics must be the same everywhere. And everything else is just a logical step from these 2 points, but getting used to those ideas that result from the logical steps will take a little while to settle in. So for now, from the previous 2 videos, it's just important to remember 2 things. The first is that space-time diagrams, they show us how space-time looks relative to a stationary observer, and we can use that space-time diagram to also figure out how space-time looks from the point of view of an observer moving with a relative velocity v. And we'll come back to these space-time diagrams and look at them in more detail a little later. And the second thing is that simultaneity is relative. So whether or not 2 observers agree that events occur at the same time depends on how fast they're going relative to each other, or relative to the events that were occurring. So in the next few videos, we will look at some more of the interesting strangeness, the interesting behaviour of space-time and of physics at relativistic speeds.